Okay, so now about the fundamentals of circuit design for AI/ML. So that's quite a switch. Just a very quick word about me. I got my bachelor, master, and PhD degrees not far away from UC Louvain. Then I made a quick tour by Switzerland for my postdoc, and then I'm now an assistant professor at Delft University of Technology. So my research interests are hardware accelerators for AI and machine learning, neuromorphic engineering and brain-inspired computing, and hardware algorithm co-design, and in a broader sense, low-power digital integrated circuits. So that's really going to be my pleasure to tell you more about those today. So first of all, if you're not yet fully familiar with AI and machine learning, let's quickly see what this is about. So then there are two main design schools. The first one is the traditional machine learning approach. So your goal is to classify your inputs based on some features, some relevant features. So let's imagine that you want to classify an image of a bee. Some relevant features to detect whether this is a bee or not might be, does it have wings? Does it have a stripe pattern? Does it have antenna? But this is much broader than that. If you have temporal signals, this can be any specificity, some temporal correlations of your signals. This can be any texture of your image, or if you are doing navigation, this can be any property of your path. So the bottom line here is you need feature engineering. And for that, you need engineers who have insight into your task to know what is the relevant feature for your task. And so this is kind of an art, because this will condition the ability of your classification here to do a good job. The other school is modern deep learning, and this is about most of the work being done today. And the whole goal is to get rid of this need for insight into your task and feature engineering. Now you get a whole black box that is an end-to-end black box model from your input to your output, and you want to derive your parameters from your data. And the key thing is that it needs actually a lot of data to figure out your features from the data itself. So as an example, this is the ImageNet dataset, which is a very famous dataset that contains about 14 million images that can span objects, animals, vehicles, and so on. So this is a very broad dataset, and even it could be considered quite small by modern standards. And to derive your features from your data, to learn your model from the data, you actually need to run this dataset multiple times to your network. So this is something that is extremely expensive. And so this approach of modern deep learning only started taking off in 2012. So this is a big turning point for deep learning, because look at what happened. So here you have over the years from 2010 to 2015. In blue, you have the traditional computer vision, so the traditional machine learning approach with hand-engineered features. And in green, you have the deep learning approaches. And look at 2012. Actually, here the green points were a big enabler. It is because these are the first GPU-based deep learning approaches. And so why GPUs? If you actually compare the performance of your GPUs compared to the CPUs, so GPUs stand for graphical processing units, just as the ones that you have in your laptop or your main computer, you see that the performance is actually much better than the CPU. And so why so? Well, the bottom line is that the catalyzer of the deep learning revolution is proper hardware. And the whole tutorial today is going to be about what is proper hardware for AI and machine learning. So we are actually going to come back to this figure a bit later. So here's the outline for today to figure this out. Let's first start with the basics and the key design decisions. Then we'll go on to the parallelism and data reuse, so some key elements that you are going to play around with. Then we'll go to memory hierarchy, hardware architecture, and data flow. Then the big, broad realm of hardware algorithm co-design. And finally, we'll wrap up. So let's start. Basics and key design decisions. So I want to come back to this big black box and see a bit what's inside. So of course, you have your input and you have your output. So these are several units. And these units there at the input can typically represent the pixels of your image. And the output units can typically represent the class that you are going to infer from this image. So how likely this image is to be a dog, a cat, or an insect. So the whole magic of deep learning is about doing weighted sums. So you are going to add another layer of units, with the blue links here representing the weights, and each unit is going to do a weighted sum of all the inputs. Second ingredient, you are going to add a nonlinearity. So every unit is also going to do a nonlinearity after this weighted sum. And here I have illustrated the ReLU, or rectified linear unit. So you only basically get rid of the negative values that you clamp to 0, and you preserve the positive values. So this is a popular one, not the only one, but one that you will come across quite often. And the whole magic of deep learning is doing that n times. So you end up with n layers and a deep network. And yeah, so now let's try to do something useful with it. So the whole process of propagating your information from the input layer by layer until you get your output values, then you are going to see, okay, which output unit has the highest value, and then this is going to be the task that I'm inferring from my image. The issue, so here this is a process that's called inference, but the issue with it is that in order for this network to do what you want, you need to have the correct weights. Because if you initialize your network randomly, you are going to have a random decision. For example, your network might say that this image represents a dog. Of course, this is wrong. The correct answer would be an insect. And the whole process of starting from this error, going backwards in order to nudge the weights in the direction that reduces the error, is the training. So now, disclaimer, this tutorial is not going to be about training. So we are going to assume that you have a network that has been trained in advance, and you only want to do inference. But I'm going to add a small note on training later on. The important thing to remember is that all the ingredients that I'm going to mention for inference, you can apply them to training too. Okay, so now time for a little bit of math and symbols. So let's give it some symbols. For every layer, the weights you see are going to have the W symbol with the superscript representing the layer index. And the outputs of each unit, which are denoted as activations, have the symbol Y with the superscript representing the layer index. So you have that every layer is doing this computation. Every output is a nonlinear function of a weighted sum of the output of the previous layer. In the general sense, you will have typically a bias term, but we are going to ignore it in this tutorial because without loss of generality, it's actually very easy to implement. So now let's look at a different way to see this core matrix multiplication that is actually the very core center of what you have to accelerate. You have here a big weight matrix, and on one side you have a dimension that is the number of inputs. On the other side, you have the dimension that is the number of outputs. It makes sense to have a weight matrix from an input layer to an output layer that has the dimensions of number of inputs and number of outputs. So that's one matrix. But you see here that the output from the previous layer has obviously a dimension here, the number of inputs, but then it has another dimension that is called the batch size. So the batch size is just how many inputs you are going to process in parallel. So in that case, that would be how many images you are going to provide to the network and to classify in parallel. And of course, if you provide n, so in that case, b images in parallel, you would have b outputs in parallel for every layer. Good. So now, bottom line number one, this is all about parallelism. This is all about parallelism along any dimension of the outputs, m, inputs, n, and batch size b. We are going to come back extensively to that. Another question is, what is the trade-off of managing such a network that can reach a size of gigabytes? Of course, you need to access your data efficiently. And so the whole magic for that is as you only access data when it is truly necessary. You access it once, you do as much computation as you can from this data before discarding it and getting the other data. So this is what is known as data reuse. That's tip number 2. And tip number 3 is you need a memory hierarchy that is able to support these specific access patterns to your data, which is known as Dataflow. So this might not seem super clear just yet. And just remember, these are the 3 main tips that we are going to clarify all along this tutorial. Good. So to do so, we are going to focus specifically on this matrix multiplication and go to the next point of the presentation, which is parallelism and data reuse. So the first 2 tips. So now let's simplify things a little bit. We are going to look at a single layer and have a look at the color code. The inputs are going to be in green, the weights are going to be in blue, the outputs are going to be in orange. You'll notice a few differences compared to the full equation that you had before. Now the outputs are denoted as Z because we have removed the nonlinearity. So to avoid confusing, it's not Y anymore, it's only Z. You have to remember that you need to add the nonlinearity afterwards. And because we only look at a single layer for now, we got rid of the layer index and we use as a superscript B, which is for the batch index. So you do have all dimensions. You have the index J that is for your outputs, you have the index I that is for your inputs, and the superscript B that is for your batch size. And so now we should actually be ready to have our first hardware for AI. So let's draw this. Actually very simple. You only need a memory and what is called a MAC unit. A MAC unit for multiply and accumulate. So this is what is shown in the title. You only need one single MAC unit and you can do matrix-matrix multiplications. So that's easy. You just need to actually access all of these operands, and every cycle you add a contribution to this output. So this is actually what you do, is you have here a partial sum that you are going to update until you have processed all of your inputs. So let's do this step by step. So you are going to have first a processing this link here. So you see Y0, WJ0, and so on for every input unit one at a time, until actually you have accumulated your final output, so you can remove the little tilde that was representing a partial sum, and you have actually your full output except the nonlinearity. So you can do that sequentially for your whole network, for your whole layer there. And so the thing is that you need to do that n times m times b times in order to compute your full layer. And that needs that many write accesses to your memory because you need to store your partial sum at every cycle. And 3 times more read accesses because you need to access the 3 operands at every cycle. So this works, but this is far from efficient due to something that is known as the von Neumann bottleneck. You are accessing your memory every time and you do not reuse anything. And so let's see why this is a von Neumann bottleneck and we want to get rid of it. So imagine that your memory here is external memory like DRAM. You are going to pay roughly 1 nanojoule of energy to access an operand, while actually computing with those operands is only going to cost you 1 picojoule. So it's a difference of 3 orders of magnitude. So accessing memory is expensive and computing is actually cheap. So let's see how we can do better. And actually, because this is slow and power hungry, the only way to deal with that is to put our 3 tips into practice: the parallelism, the data reuse, and the memory hierarchy for the data flow. So let's start with the first tip and see what it's about. So in the general sense, you can process your layer, and that's the very naive way, so that's a disclaimer. Let's do parallelism the naive way first. You can, in principle, do any of these input weight multiplication for any pair of unit in parallel. So here I have denoted like these 2, here these 2, and here these 2 for different sets of indices for inputs, outputs, and batches. If you do so, this is great. You're going to have p units in parallel. So you are going to have a throughput that is multiplied by p, assuming that you can fetch all operands in parallel. So this is a big assumption, and I'm going to come back to that. But you see that the number of memory accesses is unchanged. You are going to have less cycles, but at each cycle you are going to access more data. And so actually it is not going to help for the energy footprint. To help with the energy footprint, we need to put our second tip into practice, which is tip number 2, reuse your data. And the easiest way to do so is actually to look at each dimension individually. So let's parallelize first along the batch dimension. So it would look something like this. Every same pixel of the different images in your batch are going to be processed in parallel. So let's do this. Let's start from our initial hardware. Now we are going to parallelize it. And you see that the superscript of the batch index is increasing. And now you see that magic happens. You only need the same weight to process all of these operands. And there are 3 ways to see this. One is in your hardware diagram. The second one is here in your network diagram. You only need the same weights to process all of those. And also in the equation, because the weights do not depend on the batch index. So these are 3 different ways to see the same thing. And so good news, that means that the memory fetches for the weights can be amortized. You only need to fetch it once, and then you can reuse it. So that means that the equations for the number of read accesses and write accesses that we had before actually become this, where the weights are going to be amortized along the batch dimension. And so that's for the batch dimension. We can, of course, go with any other dimension, so let's do it right now. Let's now go for the output dimensions. That means that we are going to process our outputs in parallel. Good, we have our circuit. We are going to parallelize along that dimension. So you see that now we are parallelizing along the output index here, and now magic happens. You see that the one that is in common is the input, which you can see again from your circuit, from your network diagram with only the same input that is projecting to both outputs, and also in your equation because your input does not depend on the output index j. So that means that now we can amortize our input. So that means that our required memory accesses are going to be reduced for the inputs along the output dimension. So now, sure, you are going to tell me, let's do that for the inputs now. Let's parallelize across the inputs. We are going to do this right now. We can expand our circuit to parallelize now along the input dimension. So you see that the input index there, you see that now you only have one output that you can share. Great, you can amortize those. And actually, we are totally wrong because we went too fast. We got a little bit too overconfident. So actually, let's take our time and see what's happening. You're fetching one partial sum here for every single Mac unit. But the issue is that every single Mac unit is adding a different contribution to your partial sum. So that means that at the output, you do not have one partial sum, but 4 different ones, because all of them contains a different contribution. So let's take just a little bit more time and take time to draw this nicely. And actually, you see that the only thing that you need to do is to just make a shortcut and provide your partial sum directly to the next Mac unit. And now you see that you only need to access one partial sum and to store one partial sum. So that works still. Required memory accesses, you are going to do the savings for the read accesses along the input dimension. And good news, now this also works for the write accesses. So now a small disclaimer. We have gone through the B, M, and N dimensions. These are not mutually exclusive. You can combine them. So that's for one. But we still haven't talked about 2 big issues. So one is the memory bandwidth. We are still assuming that we can fetch all of these operands in parallel. And the second one is that actually we have quite a big critical path there. So these are 2 issues that we have not solved yet. And we have learned how to do data reuse, to save energy. But as a hint, there's still a tip left. So let's go to that part of the presentation and involve the memory hierarchy and the hardware. So let's come back first to this von Neumann bottleneck. If you're familiar with computer architecture, and just to remind the orders of magnitude, our goal is really to solve this 3 orders of magnitude different. And now if you are familiar with computer architecture, you know that modern processors are not anymore about fully separating the processing and the memory, both well separated on 2 sides, but actually the modern processors have a memory hierarchy. So you see that actually your memory, external memory, is going to cost 1 nanojoule per access, but now you have many layers of memory down to your core. So the smallest level of memory is a register file, typically just a few kilobytes, and this is very cheap to access, typically on some flip-flop cells. So this is 1 picojoule per access, very close to your compute. And then you have level 1 cache, level 2 cache, and depending on the size, typically level 1 cache is closer to the core, 10 to 100 kilobytes. This is going to cost 10 picojoules per access, and the global level 2 cache is typically going to be 100 kilobytes to a few megabytes, and this is costing typically 100 picojoules per access. So we just need to do the same for our hardware accelerator and involve some intermediate layers of memory. That is going to cost from 10 to 100 picojoules, depending on the size of that memory. So we need to do also a few tweaks. You see in your Mac unit, you can also now add local memory to benefit from this locality of data and some control. And then this is known as not anymore a Mac unit. This is a processing element that includes the Mac unit, the register file, and the control. So now we can put everything into place. Here is a typical architecture of hardware for AI. So you see that you have your external memory, you have your global buffer, and you have your AI hardware there. So important design considerations. What are going to be your memory access patterns? And this is a hugely important question because it's absolutely key to figure out the data reuse opportunities, the bandwidth, and the storage needs. In other words, you cannot dimension your hardware as long as you do not know your algorithm. And that's very important. This is very algorithm dependent. So that also means that if you do not know your algorithm, you are going to have a trade-off between the flexibility and the efficiency of your system. So let me actually rewind a little bit. And so that means that for now, you have the orchestra, but you do not have the maestro. So the maestro is actually the controller that is going to dispatch this data to your hardware and to know where to reuse it, where to store the different operands, and so on. Second point, you also need to dimension this global buffer that is here. So you have several questions that you can ask. Do you want to have multiple levels of buffering, such as the L1 caches and L2 caches in the processor? Do you also want to do banking? So banking is just that you are going to have separate banks of this global buffer in parallel so that you can access multiple operands in parallel. So these are very important questions. Of course, you also have to dimension your PE array. And that's a trick question. Because if I tell you, well, you want to parallelize, I have hammered in this message, you want to parallelize as much as you can, so let's do the biggest PE array you can. The issue is that if some parts of your network are not exploiting the whole parallelism of your PE array, you are going to have a lot of unused PE elements. And these unused elements are going to add to the overall footprint due to their static power. So that comes down to hardware utilization. Parallelize as much as you can, as long as you can ensure a good hardware utilization. And finally, the overall data flow. So this is a word that I have mentioned a few times, but still never explained. So let's see what it is about. Data flow, so you have your orchestra, you have your maestro. Data flow is basically the music score. So what kind of music do you want this accelerator to play? We are going to come with a very concrete example in just a minute. But just to highlight a little bit what it's about, your operands can be stored in the external memory. They can be stored in the global buffer. They can be stored in the local register files of your PE elements. So that makes a lot to choose from. And beware that storing your operands in the PE array, this is called as data stationarity. You are going to have your operands in your PE array, and you are going to leave them there to reuse them as much as you can. So typically, you are going to store there the operands that you can reuse as much as possible. So let's do a concrete example. One of the most famous stationarity options, so one of the most famous data flow options is weight stationarity. So you have your 3 operands, and you are going to store your weights in the PE array. So this is shown here. Now, these weights are going to be the input of your MAC units inside every PE element. Second thing, you will notice that here I have kept the output index j constant, so that means that we can propagate your partial sum across a full row of your PE array. Given that we have now increasing input index in your PE array, that means that you need to provide all of these inputs in parallel to broadcast them to all PE elements. Good, sounds easy. For now, we have just stored the weights inside the PE array, propagated your partial sum, and provided the inputs. You are going to tell me, what do we do with the other rows? And that's a very good question, because you have actually several options. What do you do there? Do you parallelize over batches, over partial sums, or do you continue the partial sum? Certainly, the simplest option is actually to continue the partial sum at the next row if you need to sum over more elements, so that's the easiest one. But actually, the other ones, there's actually a very good option and a very bad option. And so let's see which is which. Hint, let's start with the bad option. So let's start to parallelize over the batch size. So you are now going to provide your partial sum over b+1 and your inputs over b+1. And you see that actually you had to repeat the weights at the next row. If you follow your equation, these are the same weights for the different batch units. So this is something that we have mentioned a little bit earlier. And so now you see that you have to repeat the weight in your PE array, which is in itself not a great idea, but that also means that you are killing the only data reuse opportunity that you had. Because what you would like to do is to store the weights inside your PE array and to reuse them as much as possible. So basically to provide the different inputs over many batches to these same weights and keep them locally in the PE array. What you would do here is to duplicate the weights and access all of them once, which is not a good idea. We are going to come back to that quite extensively. So that means that the good option is to actually parallelize over the output. So that means we are going to provide the output j+1 here. So you see that now the weights are different from those in the previous row. And that actually also bonus, you can reuse the same inputs to provide to all PE elements. So that sounds much better, but we can still do even better. So now as a hint, we have only played with space. So you have the inputs along the row dimension and the outputs along the column dimension. Can we play with time? And now, if you have listened to my explanation as to why the batches are not a good idea, this is precisely there. You would like to actually provide your batches over time so that you can reuse the weights that are stored in your PE array. This is the right way to go. So let's do this. For now, you can assume that all PE elements that are in gray are unused because we sent a 0 input to them. So we are going to take back the same ingredients, propagating partial sum and broadcasting of the inputs. So let's start with the first cycle. We are going to provide the partial sum, partial sum ZJB here, together with the corresponding input YIB here. And so you see that together with this weight there, you are going to have an updated partial sum at the output of this PE element. Important thing, now you have to see things in time. This is the output you will have at the end of one cycle. At the next cycle, you are going to have this PE element receive the updated partial sum ZJB here. So you are going to multiply this input here by the weight over index I plus 1, and you are going to continue to have the updated partial sum at the output of this PE. But meanwhile, at the next cycle, you have provided this new partial sum ZJB plus 1. So here comes the batch. Next cycle, we have incremented the batch. And we have also incremented the batch index of the input. So that means that the output at the end of the next cycle is going to be ZJB plus 1, so the updated partial sum. And so on. So you really have to see this difference between space and time. In space, we are going to always go from I to I plus 7. And in time, you are just filling your pipeline of PE elements with increasing batch indices. So later on, you are going to continue with that. Now you provide B plus 2, and you are going to have the updated partial sum still ZJB that is going through, then ZJB plus 1, and finally ZJB plus 2. And if you fill the pipeline, you end up with something like this. And so you will see that this batch index is also over time has filled the pipeline. Good, so you see the I index is in space, the B index is in time. You can reuse the same thing we have figured out at the previous slide. You can also take the J index on the other space dimension. And now you have a complete PE array that is using both space and time. And now is the time to summarize. This may not make fully sense or fully music to your ears yet, because it takes quite some time to turn all the tuning knobs. But when you revisit the slides, you will see that this is always the three same tips. It's all about parallelism, it's all about data reuse, and now finally we have figured out the last one. It's all about memory hierarchy to support your data flow. And even worse, now you see that there are plenty of options, but we have only seen the weight stationarity option in your data flow. As you can guess, you can have also input stationarity and output stationarity, and I leave those to you as a homework. So now we can go to the last and perhaps the most important part of this presentation, hardware algorithm co-design, because I have mentioned quite a few times that indeed it all depends on the hardware that you want to accelerate. So now that you're experts in the fully connected layer, we are going to get rid of it. So why do we want to get rid of the fully connected layer? This is perhaps the baseline layer for anything you will do in AI, but it has a few issues. And one of those is that between every input-output pair, you are going to have an individual weight. So this is actually a layer that costs a lot of memory to store all individual weights for all inputs and output pairs. In other words, this is known as there is no weight sharing, individual weights between every pair in inputs and outputs. So we are going to look now into the infamous convolutional layer. So for now, let's forget about the equation. Just see that the same ingredients are there. You are going to have a partial sum, you are going to have weights, and you are going to have input. Let's get the intuition first. So let's come back to our nice insect image. And now you have a set of weights that is known as a convolutional kernel, but this is just a set of weights. The only difference is that you are going to repeatedly apply this set of weights all across the image. So let's do it just now. You are going to start applying your set of weights here at the beginning of the image, and you are going to individually multiply every element of your convolutional kernel with every pixel of your image. And you are going to take the sum of everything. So what that means is that you are doing a detection of pattern overlap. The higher the overlap of patterns, the higher the output is going to be. If there is no overlap whatsoever, you are going to have a very low output. So here you see that there's not much overlap, so you are going to have a very low output. And so on. You are going to slide your kernel, And here you see that you already have a little bit of yellow that is overlapping. The output is going to be slightly higher, not very visible in this screen, but you can go on and continue. Okay, still very low overlap. Here you are starting to get actually much more yellow, so this is already half of your convolutional kernel. You already have a higher output. And so on, you slide your kernel. Now it's actually a much better match. You already have one stripe that is matching there, so you are going to have a much higher output, and so on until you actually have the best match there. It's almost perfect. You have a very high output, and so on until the end of the image. So this is really a pattern detection algorithm, basically. Good. Now, actually, you have many other dimensions that you can play with. In the general sense, in a given input or in a given image, you are going to have multiple channels. For an image, you have seen that earlier today. This is typically going to be red, green, and blue. These are going to be individual channels. But in intermediate layers of your network, you can also have many different channels. And why so? Because you can actually have multiple kernels. And for every type of kernel, you are going to have a different output feature map. And let's imagine that you have a layer that has 10 kernels. That means that the next layer is going to have an input that has 10 channels. And so why different kernels? Typically, this is going to you are going to be able to do more pattern matching. And typically, this is a kernel that sounds right if you would like to detect a tilted B. Then the pattern is going to match. So anyway, you see that this adds a lot of indices in your equation, and that becomes not so readable. So let's still forget about the equation for now. We are going to come back to it. But for now, what I want to mention is that because you are reusing the same set of weights all along the image, now you have weight sharing. And this is an opportunity for more data reuse. And we are going to see how. For now, let me emphasize this once more. If you're not familiar with convolutional layers or any new neural network layer in general, focus on the intuition first. Forget about the equation. And then this is the way to go. You will really have to go back to the equation because this is the only way to really figure out things on how to organize the mapping in your PE array. Why so? Follow these guidelines. Every index is an opportunity for parallelism. And every missing index in an operand is an opportunity for data reuse. And now you may remember, again, this batch example that I have used multiple times. The weights do not contain the batch index. And so that means that this is an opportunity to reuse your weights over multiple batches. Every missing index in an operand is an opportunity for data reuse. So once you're going for the equations, you just look for the missing indices, and this already gives you a hint as to what you can reuse. OK, so now we are going to do this right now. Let's come back to our nice P array and now do the exercise for the convolutional layer. So you are going to have, again, the broadcasting of your inputs and here the propagation of your partial sum. Good. So now let's start figuring out along which dimensions we can parallelize and along which dimensions we can reuse. So here you see that for the inputs, you can parallelize over the C index, the M index, or the N index. And why so? Is because you have to look for the indices that are in common between your inputs and your weights. And you see that the only indices that are in common between both are C, M, and N. That means that you can pick any of them. For now, in this example, we are going to illustrate for the N index, but this is just, you could have picked other indices. So now, let's basically store your weights along the row dimensions along N. And now we have to decide along which index we are going to parallelize in the column dimension. So here you have to, let's go back there, you have to see that there are indices again that are in common between your outputs and your weights and indices that are not in common. So the indices that are not in common are B, I, and J. And you see that they are not in your weight. So that means that these are indices you do not want to parallelize over in the column direction because it would lead to duplication of your weights. This is the exact same example as we had before, trying to parallelize over batches. No, these are actually the dimensions that you want to use time for to reuse your weights. So the only choice that you have is actually the K index that you have here that is in common between your output and your weights. And therefore, you can basically have different partial sums that you provide over the K dimension. And indeed, you see that you store a different set of weights along the different rows. All good. So that means that now the B, I, and J, as mentioned earlier, there's a weight reuse opportunity that is possible by providing these operands sequentially over B. And now you also have I and J. So the big difference that you had compared to the fully connected layer previously is that the opportunity to sequentialize over time, now you do not only have it for B, you have it also for 2 more indices. So that's what the more opportunities for data reuse, and that was written in the previous slide, is coming from. You have more options. And so, yes, again, this is coming back to our 3 tips. You see that there are many, many, many options. You may feel a bit lost as to, wow, there are so many opportunities to parallelize, to sequentialize, without talking about the fact that this is still only for weight stationarity. So that means that the search space is huge. So your job as a designer is to find the best combo for your application and for your application requirements. And good news is that there are tools that help you automate the search. So you're not alone in front of this huge set of options that you can pick from. You have actually tools that allow you to automate the search. And if you know what you are doing, you are going to have an easy time using these tools. Good, so now you're probably a little bit tired with layer stuff and mapping on PE arrays, so let's leave it aside. And before closing my presentation, I'm going to mention a few more useful elements when it comes to hardware algorithm co-design, and one of them is quantization. Because instead of 32-bit operands, which I have assumed up to now, you also have that modern neural networks can be quantized to 16, 8, 4, 1 bits, and not even power of 2. Any combination of different quantization levels can be used. So to give you an example, an absolutely arbitrary image that represents a Delft campus, you're going to have the unquantized image with 8 bits per channel. It's the default image. But if you quantize to only 2 bits per channel, you see that the image is still very much workable. So you can imagine that an algorithm whose goal is to detect the trees, the pedestrians, the bikes, the buildings, and so on, is going to have a very similar performance. You're not going to lose much. And so you can do that for your input and also for your parameters. So quantization actually allows you to save a lot. That means less accesses to the external memory, so you are going to pay that 1 nanojoule less times. That also means a smaller global buffer. So that means that given that the size will be reduced, you can go most likely for the smallest access cost of your global buffer. And finally, that also means a reduced footprint and critical path for the PE array, because in your PE element here, you do not have to do a multiply accumulate over 32 bits, but much less. And to give you an idea, the MAC energy is reduced by about an order of magnitude if you reduce from 32 bits to 8 bits. And so that's very advantageous when it comes to energy and throughput at the expense of accuracy. So oftentimes you can quantize quite a lot before you see an accuracy degradation, but it all depends on your application requirements. So it's up to you to see what is acceptable. Okay, second ingredient that is also very nice is sparsity. Because for now we have assumed that you have no sparsity. All PE elements are fully busy with non-zero operands. So at least it is good for hardware utilization. You have no processing element that sits idle, multiplying with a 0 and contributing nothing. Now, if you have limited sparsity, typically about 10% or so, and worse, unstructured, so typically a few random elements here and there, there's not much you can do with it. Because if you would like to exploit it, you have to tweak every single PE element with extra control to gate the PE element, and also potentially to forward data. So that's going to be control overhead for every single element. This is usually you are going to have much more control overhead than savings that you can do with unstructured 10% sparsity. Now, if you have structured sparsity, typically row or column based, for example, looking like this, then it's much nicer because this is PE array friendly. You can gate a full row or a full column, and if your controller is smart enough, you can already forward the next data to the next column, so that's very nice. And that's also straightforward in terms of memory savings. And finally, what about very large sparsity? Like, what if your operands or inputs or weights are 90% sparse? So typically, you have to remember that here you have a nonlinear function. I have illustrated previously the ReLU, so that cuts all negative values. So that means that typically in a ReLU network, your inputs are going to be about half sparse, 50%. If your training is smart, you can tweak the learning in order to have, for example, very large sparsity. So this is not such an uncommon case if you're looking for it. So what do you do with very large sparsity like this one? You can compress the storage very nicely in memory, so that's one good thing. But you need to be very careful in terms of data flow to still leverage parallelism. And so how so? Here's an example where actually you have a data flow that is tweaked so that the same input value is broadcasted to all the P elements of a given row. And now you may already have seen that the color code is a little bit different. It's because here I have illustrated an output stationary data flow. So I mentioned earlier this is for your homework. But if you're looking for clues on how to solve this homework, you know that in this slide you already have some indications. But also some of you may have heard about event-driven computation. This is typically the kind of data flow where you have one input at a time that can go very well with event-driven computation. Okay, last one before I wrap up is heterogeneous architectures. Because, let's make a bit of space, because good news, there is a life beyond PE arrays. There's not only PE arrays, you have many other options. Some of those are the in-memory computing approaches. So these look roughly like this. The whole idea is that for now we have tried to bring the compute as much as possible, as close as possible to the memory, as close as possible to the compute. And in-memory computing is doing exactly that. It's actually carrying out the compute inside the memory, so you need specific memories for that, or very nearby to the memory with some near-memory logic. And state-of-the-art designs can achieve efficiencies that are as good as 1 to 10 femtojoules per operation. So this is extremely good. Another option, you can have specialized accelerators because not everything is going to be well parallelizable on a P array or an IMC array. You may want to have some dedicated logic that is doing, for example, a complex nonlinear activation function. So you are going to have a specialized accelerator that is there. And now comes this flexibility efficiency trade-off that I mentioned earlier. It depends a lot on how much flexibility you want to have to map your workload. If you know that you're only going to execute one kind of network, that's very easy. If you want to have a general purpose AI accelerator, then you need to account for some flexibility. And therefore, that also means that you need typically a processor, a general purpose processor that can handle whatever workload appears in the future that your AI accelerator may not have been planned for. But that also means that this processor is going to have an efficiency that is much less than your P array or your IMC array. So beware, it is about system-level optimization and not macro or block-level optimization. And so that brings me to the last point. Be very careful with the tera operations per second per watt. So this is read as TOPS per watt, but this is really per second per watt, or in other words, tera operations per joule. So this is an efficiency metric. And the first caveat is that if your computing efficiency is amazing, like in your IMC array, it is 1 peta operation per second per watt that you have there with your 1 femtojoule per operation. But if you burn 1,000 times more energy bringing your memory from the DRAM directly to your macro, this is useless. So you can only overshoot in your compute efficiency as long as your memory hierarchy is at least as good. Otherwise, you're over-optimizing. Second point is, what about, so not all operations are created equal. A 32-bit operation is, of course, going to cost much more energy than a 1-bit operation. So be very careful, tera operations per second per watt, at which resolution is a very important question. And so finally, prefer task-level metrics. This is the only way to be fair across systems. So typically, these task-level metrics are going to be energy per classification, latency to decision, and beware also that these only hold for a given task at a given accuracy level. So you can imagine that carrying out a complex task at a very, very low accuracy is going to be much cheaper than carrying out a complex task at a very high accuracy. So be careful about all of those, but if you compare with the same task and the same accuracy level, comparing those metrics can compare any kind of system. Whatever it contains, this is always fair. Good, so time to wrap up. So if you have to remember one thing about this talk is the key tips. So parallelism, data reuse, and memory hierarchy for data flow, you can deal with any new fancy thing in AI if you are familiar with those. So let me add one more. Tip number 4, use hardware algorithm co-design to track the bottlenecks and reveal the new opportunities. And this is really going to make you independent because innovation in AI goes extremely fast. And so this will allow you to deal with the new stuff that is popping up. So also the key questions that you would need to look at, there are many categories, so this is basically a short summary. First, at the application level, everything depends on your algorithmic workload and your specifications. A choice might be valid for a given specification that is not valid for a very different use case or specification. So what are your specs? What is your algorithm? Are there co-design opportunities? Are there opportunities for sparsity? What is the trade-off between flexibility and efficiency? So how known your application is. Second, the memory hierarchy. So how much do you know about the memory access patterns? How do you store your operands? What are the levels of buffering? Third, the hardware architecture. So which accelerators? So we have seen the P arrays, the IMC, the dedicated accelerators. So which combo do you need? And what is the reconfigurability that you need in the P array? And making a P array more reconfigurable is going to add control overhead. And so finally, data flow. So which operands can be reused, which ones can be broadcasted, which ones can be parallelized, and which ones should be kept stationary. So overall, I have highlighted how large the search space is. And so good news, I mentioned these tools earlier. So these are called design space exploration tools. And there are quite a few of them. I have listed a few. I'm going to list them also, the public repositories, if you want to play with those. And so you're not alone. You can automate a big part of the search. And if you know exactly what you're looking for, you're going to have a much easier time. Also, what you can explore after this talk, if you want to play around, many things I haven't talked about. One of them is more neural network models. We have only seen the fully connected layer and the convolutional layer, so they are also out there. Recurrent neural networks, transformers, state space models, so all new fancy things that require new hardware. Alternative computing paradigms. So you may have heard about neuromorphic and brain-inspired computing, also stochastic computing, mixed signal processing. For now, we have assumed that everything is digital. But if you do computation also in the analog domain, it's typically at low resolution, you can also save a lot. And also physics-based and memory-stive computing. So playing with new devices also to save on your efficiency matrix. Also, on-device training. So this is the thing I mentioned this tutorial would not be about. So all these recipes, you can apply them for training on the device. And what kind of training do you want? Do you want to do only fine-tuning on the accelerator? Do you want to do low-footprint training? And you have a lot of research on training data flows. So all these ingredients come back for training as well. Also, system-level optimization. And now, because I have mentioned heterogeneous architectures, these are architectures that have a lot of complexity. So you also need good tools, such as good mappers and good compilers to actually exploit your hardware. So now I can come back to this figure that I have shown earlier, because I haven't mentioned what is the GIE here. GIE stands for GPU Inference Engine, so this is a misleading name, but this is just basically the toolkit that NVIDIA is providing. So this is a software framework whose only purpose is to say, okay, give me an application, I'm going to find you the best mapping for my GPU. And you see that with the proper tool, the hardware is much better utilized. So there's no hardware innovation there, it's just better software. And that also means that if you have very badly developed software for fantastic hardware, you are not going to have good metrics. So don't underestimate the importance of doing good software when you design hardware, because indeed, actually developing good software also takes time. So that underlies the importance of having a good team. And so all of these highlight new opportunities for hardware algorithm co-design. And let me finish by just pointing to a few useful resources. First, there's this classic, which is this tutorial paper I have listed here. Also, a survey on hardware algorithm co-design, and now a few open source repositories. So the design space exploration tools I have mentioned earlier. And now there's not much open source hardware out there. So I have listed two. The designs by the PULP team. So PULP stands for Parallel Ultra Low Power. And so you have these, all the designs from the PULP team that are listed there, and also an earlier design of mine that is open source with an online learning RNN accelerator. But what that means is that we need more contributions to the open source hardware community. So if you go to that field, consider contributing. Thanks for your attention.